Okay, so welcome to the 11th lecture of computational complexity. And as already announced on the forum, the main result we're going to look at today is a rather surprising result, a stunning result almost, because it's far from obvious. The two classes seem so unrelated at first sight. And that's proving that the class of languages that can be given interactive proofs in the sense that we considered 2 lectures ago is equal to PSPACE. So every problem that can be decided in polynomial space can be given an interactive proof. And if a problem can be given an interactive proof, then it can be decided in polynomial space. Maybe at first sight, one might think that the most surprising thing here is that if a problem can be given an interactive proof, then it can be decided in PSPACE. And the reason one might think that that is surprising is that when we defined the PSPACE problems, they involved a PSPACE protocol involved an interaction between a verifier that was polynomial time and a prover, where the prover was allowed to use arbitrary, unlimited resources in order to participate in their side of the interaction. So the prover did not need to satisfy any complexity bounds at all. And so you might think that, well, if you've got a language in IP, there's almost no reason to expect it to lie in any complexity class at all, because it involves some magical prover that can basically tap into mathematical truth and not do things in a computational way. But as we shall see, it is not that hard. I mean, we'll not go into every detail, but it actually turns out not to be that hard to show that if you have a problem in PSPACE, then you can find a prover that can prove the problem where the prover only uses polynomial space. And we'll see how that works. And once one's got that, well, basically the argument that one uses to show that also shows that the whole class of interactive proofs are in PSPACE. And that actually turns out to be the easier direction of this equality. The harder direction of this equality is to show that PSPACE is included in IP. That is to show that every language that can be decided in polynomial space has an interactive proof. And actually this came as a really big surprise to researchers in complexity theory at the time it was developed. I think the late 80s or the turn of the 90s, something like that. Because when the class of interactive proofs was introduced, people were giving interactive proofs for rather languages very low in the polynomial hierarchy, things like graph isomorphism and the complement of graph isomorphism and so on. So these are languages that are in NP or co-NP, but are not even thought to be NP complete or co-NP complete. And people thought that actually interactive proofs would only be available for languages of relatively low complexity. So actually it was a very surprising result for people when actually they discovered that interactive proofs are one could be sufficiently clever in an interactive proof that one can give an interactive proof for every PSPACE language. Okay, so to set the scene, we need to remember what polynomial space is. Good morning. So we're going back actually to lecture 5. We defined polynomial space, but I mean, I think we've been dealing with that enough that I don't need to go over the definitions again. But what I want to do is recall basically the situation we were in the last lecture that we talked in detail about polynomial space was lecture 6, and the goal of lecture 6 had been the intended goal was to show that the particular problem of deciding the truth of a quantified Boolean formula is a p-space complete problem. In fact, an NP space complete problem. It was also a p-space problem. And therefore, from those two results, we obtained that p-space equals np space, and also that Tqbf is both np space complete and p-space complete. So that's where we were, except that we did not complete the proof that the truth of quantified Boolean formulas is an NP space complete problem. We proved that it's in P space, so hence in NP space, but where we stopped was in the proof that it's NP space complete hard. So we didn't complete the proof that any NP space non-deterministic polynomial space language can be reduced to Tqbf. So today I want to begin by completing that proof. It was actually in the notes for the lecture. I don't know how many people read through it, but it's a nice little argument, this, so I do want to go over it. This was in the notes for lecture 6, but I do want to go over it to start with today. So we'll do that first. And once we've done that, we'll address the first of the inclusions between IP and P space. We want to prove that IP equals P space. We're going to prove two inclusions. So the first one we'll do is the easier one, which as I already said, is the one you might be most surprised with at first thought, because of the fact that IP is defined with allowing a prover with arbitrary computational power. Yes, and for those of you taking notes, I'm sorry if I go too fast through, but these notes are going to be published obviously online, but you're welcome to take your own notes. So we'll show that inequality first. So this was actually an exercise in the exercise class, not last Friday, but the Friday before. But you didn't, Danelle told me you didn't have time to get to this exercise. So that's why I'm putting a proof in this. I think you did the exercise before, but you didn't quite get to this one. So that's why I'm putting this in the lecture. And then we want to show the other inclusion. And for the other inclusion, we want to show that every P-space language has an interactive proof. But perhaps unsurprisingly, and we'll see what the reason is, but it's a very straightforward reason, perhaps unsurprisingly, to do that, all we need to do is show that one P-space complete language has an interactive proof. So we've seen now in the student presentations, we've seen quite a few P-space complete languages, but we'll use, again, truth of quantified Boolean formulas as the language, and we'll show that this has an interactive proof. And it follows from that every P-space language has an interactive proof. So therefore, IP is included in P-space, hence equal to P-space. Okay, so that's the overview. Right. So just to remind you, the Tqbf problem, the problem of deciding if a quantified Boolean formula with no free variables, so every Boolean variable is inside a quantifier, the problem of deciding if such a formula is true. I should have a question mark. Is phi true? Okay, or as a language, the language of closed, that means with no free variables, quantified Boolean formulas, and that are true. And just to remind you what a quantified Boolean formula looks like, well, you have quantifiers for all or exist, you're quantifying over Boolean variables. And without loss of generality, and you did this in the exercise classes, I think, as I remember, I didn't double check actually before putting this in, but you can look at formulas where you just have the quantifier prefix on the outside, so-called premix normal form formulas. So you just have a quantifier prefix on the outside. So here, Q1 through to QK, each one of these is either a for all or an exists. And then inside, you need a propositional formula. But by using the Tseytzin transformation or some other transformation, you can also get this propositional formula into 3 conjunctive normal form, you might need to stick some existential quantifiers in here, but then they get absorbed into this quantifier prefix in order to do that. And without loss of generality, the Tqbf problem is equivalent to deciding the truth of a quantified Boolean formula in this Pranek's normal form, where the inner propositional formula is a 3 conjunctive normal form formula. So a formula in which a conjunctive normal form formula in which each clause has at most 3 literals. Okay, we're actually not going to need this observation that we can restrict to these formulas just yet, but we will a little bit later. Right, so I want to go back to the proof from lecture 6 that true quantified Boolean formulas are NP. Deciding the truth of a quantified Boolean formula is NP space hard. So that means, of course, that if we have a language that's non-deterministic polynomial space, L, say, then we have, what we want to show is that there's an efficient, that is a deterministic polynomial time reduction to the language Tqbf. Okay, so to do that, I'm going to rather quickly go over the bits we already did in lecture 6, just because I can't just come right into the middle of the proof and expect you to follow. So hopefully now this is going to be familiar enough, because you've seen the start of it once and you've looked at similar things in the exercise classes. So suppose we've got a language that is NP space. So it's decided by a non-deterministic Turing machine, and the space will be bounded by some polynomial then in the size of the input word. And what we're going to do is we're going to cook up means come up with, it's a sort of English idiom for come up with, we'll produce a quantified Boolean formula with no free variables that is going to search for a path through the configuration graph of this Turing machine M on input word W. It's going to search for a path from the start configuration to an accepting configuration. If it finds such a path, then of course the non-deterministic Turing machine accepts the word in the language. If there is no such path from the start state to an accept state, if all paths end in a reject state, then of course the non-deterministic Turing machine does not accept the input word. So the configuration graph is going to be important, and we want to simulate, we're going to want to simulate looking for a path through the configuration graph by using a quantified Boolean formula. So the quantified Boolean formula is going to be true if and only if there is such a path. And because we're trying to make this a deterministic polynomial time reduction, that quantified Boolean formula needs to be constructible. We need to be able to construct it from this non-deterministic Turing machine and the input word in deterministic polynomial time. So in particular, the formula itself must only be at most, must be a polynomial size in the size of the Turing machine. So the configuration graph and the input word. So the configuration graph, we're looking at a Turing machine that we're interested in the space complexity. So with the space complexity, we've got these working tapes, and we, well, this is polynomial space, so it doesn't matter whether or not we count the input tape or not. It's not so important compared with logarithmic space. It was very important that only the working tape went into the space. For polynomial space, it doesn't really make any difference. But in any case, we've got the input tape and some working tapes, and the configuration graph is just the directed graph whose vertices are configurations of the Turing machine. So a configuration of the Turing machine will be the state, the input word on the input tape, which doesn't change, and all the words that are on the K working tapes, and each of these will have length at most. Well, we've got a total amount. The total amount of space we're using is P, which is our polynomial bound that we assumed at the start, polynomial bound that n is guaranteed to stay within. So the total amount of space used is P of length of W. So certainly each of these words will have length at most P of length of W. And we might as well, we can include some blank symbols if we want, just to make all the strings the same length. So the vertices of the graph are the configurations, and the edges of the graph are, we have an edge, we have a transition, if you like, in one direction, an edge. So this it's a directed graph, an edge in one direction from one configuration to another, if the Turing machine M can make a single step of computation from the configuration C to C prime. And I don't want to go over this in more detail. There were a couple of slides explaining this in week 6. But the important thing is that we want to simulate this configuration graph using a logical formula. And we're going to, in the end, find a quantified Boolean formula that will be true if and only if there's a path through the configuration graph from the start configuration to the end configuration. But to begin with, in order to encode that, we just want to find a formula that is going to encode the edge relation of the configuration graph. So we observed that every configuration can be encoded by a string of zeros and ones, a binary string of length big O of P of the length of W. Because that's how much information there is here. And we went over this in lecture 6. So the big O here, I've just put the constant in explicitly, so some constant times P. So it's polynomial in the length of W, but it's the particular polynomial P we've got, so it's some constant multiple of that. That's enough, how much information we need to encode one configuration. And so to encode a binary relation, an edge relation between two configurations, it's enough to have a formula with, so if we call this value capital N, the number of bits we know we need to encode a configuration, then we can encode a relation between configurations, that's the edge relation between configurations, using a formula with two times capital N propositional variables. So the point is this formula will be true for a given n-bit string here and a given n-bit string here, if and only if there's an edge from the configuration encoded by this edge string to the configuration encoded by this edge string. And in fact, using the same sorts of ideas we used in the Cook-Lievin theorem, so proving that SAT was NP hard, using the same sorts of ideas, we can find a propositional formula that expresses this with these 2 times capital N propositional variables, where the size of the formula is linear in N. And for every bit string of length N, then the formula is true. This is just saying it really encodes the edge relation of the configuration graph. So a formula will be true on 2 bit strings of length N, if and only if A is the encoding of one configuration, B is the encoding of another configuration, and for 2 nodes, C and C, C prime in the configuration graph. So for the 2 nodes that are encoded by A and B, there is an edge between them. So this is just saying the formula really does express the edge relation of the configuration graph. So let me just pluralize the node. Sometimes it seems strange for me in English to use a plural when there are only 2 things nowadays. So used to thinking differently about 2 things from Slovene. Okay, so I'm going to take for given that we've got this formula phi of the Turing machine M that we started with and the input word W. So that determines, we're interested in the configuration graph on the input word W, and we're going to the formula that expresses the edge relation from that. And now what I want to do is construct the formula that we want that says there exists a path from the start configuration to the end configuration. And we're going to do this by building up some formulas inductively in I. And for each I, we're going to say this formula. So U is going to encode one configuration, the V variables encode another configuration. And this formula is going to be true if there's a path of length 2 to the I from the U configuration to the V configuration in the configuration graph. And this formula is going to have the important feature that the size of psi I is polynomial in I and N, and we can construct the formula easily by a deterministic polynomial time Turing machine. And this says the property I've already said, that the formula is going to be true for the encoding of two configurations if and only if there's a directed path from the first one to the second one of length 2 to the I. And once we've got this, we've got the p-time reduction that we want from our language L to true quantified Boolean formulas, because we simply input the input word W, which is a word in L, and then for that input word, we construct the formula psi n. So remember, psi is determined by the Turing machine M and the input word W. We construct because that determines the configuration graph. We construct the formula psi of n, where n was the number of bits we're using to encode a configuration for an input word W. So this formula psi n, if we plug in with start and accept, it's saying that there exists a path of length 2 to the power of n from the start to accept configurations. But if you remember how we encoded the configuration graph, I had this feature that when we get into an accept configuration, we loop on the accept configuration. And if there's a path from start to accept in the configuration graph, if there's any path, well, there are only the configuration graph, each configuration is encoded by capital N bits. So there are at most 2 to the n different configurations. And if we have a path from start to accept, we can remove any loops from the path to get a path that doesn't have any loops. So that's going to go through each state at most once. And so that can have length at most 2 to the n. And if there's a path of length less than 2 to the n to accept, then once we get to accept, we can keep on looping until we get to length 2 to the n. So we have that there's a path of length 2 to the n if and only if there's any path at all from start to accept. And there's a path from start to accept in the configuration graph. Well, this configuration graph was the graph of configurations of a Turing machine M that accepts the language L, that recognizes the language L. So there's a path from start to accept if and only if the word's in the language. So we've done the reduction. We see that words in the language, if this, so this is I should have said somewhere that this is, yeah, it's the point is these are quantified Boolean formulas. So we've got a reduction to a quantified Boolean formula, namely this one, psi n, capital N, and we just need to decide then if we're reducing to Tqbf and we want to decide whether psi n of start accept is true, and then we decide whether W is L. So W belongs to the language L. So that is our reduction. Okay, any questions on that? Right, so the interesting thing then is, well, and this formula has size polynomial in n, which I already said. So the interesting thing now is how to construct psi of I. Just out of interest, did anybody read this in the lecture notes or? Right, okay, so one person has read through this. Okay, well, sorry, so this is repeating stuff that you've done, but anyway, let's finish the proof. It's a lovely little observation the way this works, I think. So we need to construct this formula psi I, and this is done by induction on I. So when I equals 0, well, psi I is saying there is a path from U, the configuration encoded by U, to the configuration encoded by V of 2 to the I steps. Well, 2 to the 0 is 1, so we're saying there's a path of 1 step. In other words, there's an edge from U to V. So for that, so the psi 0 formula we already have. We already have it. It's just a propositional formula. It's our phi of m for the Turing machine m of the input word w. Okay. So the case I equals 0 we're already done, and we want to go all the way up to psi of n. N is the number of, remember, n is the number of bits we have in the encoding of a configuration. So what we're going to do is see how to go up to I equals 1, I equals 2, I equals 3. So for each I, to construct the formula for I plus 1. So for I greater than 0, we want to define psi I in terms of psi I minus 1. So when is there a path of length 2 to the I from U to V? Where if I is greater than 0, well, there's a path of length 2 to the I, if and only if there's a path of length 2 to the I minus 1 to some intermediate node, and the path of length 2 to the I minus 1 from the intermediate node. So using our quantifiers, our existential quantifier, we could say there exists, we use another vector of n variables. So again, this is capital N variables, the number of variables we need to encode a configuration. We simply say there exist n Boolean variables such that we've already got the formula for 2 to the I minus 1 steps. So we need 2 to the I minus 1 steps from U to T and 2 to the minus 1 steps from T to V. So that would be a nice solution, except it has the problem that we start off with the formula phi, and at every step, the formula doubles in size because we're using a conjunction. So this, once we apply it n times, we get 2 to the power of capital N times the size of the formula that we started with. And that's the formula size. So then the formula size is growing exponentially. So that doesn't work. But the idea is still right. We want to say there exists an intermediate state that we can go to in such that we can get to the intermediate steps in 2 to the I minus 1 steps, get to the intermediate state in 2 to the I minus 1 steps, and get from the intermediate state to the end state in 2 to the I minus 1 steps. So that idea is right, but we need to find a way of avoiding the exponential blowup. And the lovely idea of who was it? Stockmayer and Mayer, who proved this in the first place, was how to use sufficiently many quantifiers for a true quantifier, for a quantified Boolean formula, in order to express this without the blowup. And this is the formula here. So let me shrink it a little bit. So the formula is saying that we want to say there's a path of 2 to the power of, okay, I'm defining psi I plus 1 in terms of psi I, but anyway, never mind. So we want to say there's a path of 2 to the I plus 1 steps from U to V. So we want to say there's an intermediate state such that there are paths of 2 to the I many steps from U to the intermediate state T, and from T to the intermediate state V. So indeed, we say there's an intermediate such state. But how do we say that there's a path of 2 to the I steps from U to T and from T to V without repeating the formula psi I? Well, the idea here is we do that by using psi I once and quantifying over some new variables, some new vectors of n variables, r and s. We want to say, what we're going to say is that for all vectors of states r and s, there is a path of length 2 to the I from r to the s, as long as one of the following two cases holds. Either r is the state u and s is our intermediate state t, or r is our intermediate state t and s is our destination state v. So we want to say for all r and s such that if one of those two conditions holds, r and s are as specified in these two ways, then we have a path of 2 to the length I. And we can say that using just propositional logic, that condition, because we've got the if and only if in propositional logic. So the by implication, r implies u and u implies r. So this acts as an equality between these two, an equality condition on these two lengths of variables. And this disjunction is exactly saying what we want. We either want r to be our source state u and s to be our intermediate state t, or we want r to be our intermediate state t and s to be our destination state v. And in either of those two cases, we want it to hold. So there's an implication there that there's a path of length 2 to the I from r to s. Okay, so this is the step case for defining psi I plus 1 in terms of psi I. And we see that the size of psi I plus 1 is the size of psi I plus a constant amount of stuff. Every time we're adding the same length of stuff to it. So if we iterate this n times, we start off with psi 0, which was just phi. And then n times we're adding a constant amount of stuff to it, but the constant amount of stuff includes 3 new quantifiers. Well, actually not 3 times n new quantifiers, and that works. So it's a polynomial formula in the size. It rather clearly says the same thing as this, and so it does the job. Okay, any questions on that? Good. So we've finally completed lecture 6 now, so let's get on to lecture 11, which is today's lecture. Is it lecture 11 anyway? Let's get on to today's lecture. Right, so now we're going back to interactive proofs, and we've been doing this now for 2 weeks. Last week, zero knowledge proofs, but they're a kind of interactive proof. So an interactive proof for a language is given by, it's basically given by its verifier. And what we want of the verifier is that it satisfies 2 conditions. A completeness condition that says there exists a prover that is able to convince the verifier with high probability that any word in the language really does belong to the language. And high probability is enough to, we just take as default 2/3, but as you've seen in exercise classes, it doesn't really, this 2/3 could be any value greater than 1/2, any constant value greater than 1/2. So that's the completeness. There exists a verifier that can persuade V of the veracity, that's the truth of a claim that a word belongs to the language. But equally importantly, there's the soundness condition, which is that the verifier cannot be persuaded unless it's true, or at least only with low probability can it be persuaded if the language is true, or with high probability, the verifier will reject any attempt by a lying prover to try to hoodwink the verifier into believing that the word's in the language. So formally, for any word not in the language, any fake prover P star has only a small chance of persuading the, well, it's not very formal, but we had the formal version 2 weeks ago, of persuading the verifier that the word belongs to the language. So in other words, if you've got a word that belongs to the language, sorry, that doesn't belong to the language, and you've got any fake prover trying to persuade V that it does belong to the language, V has a high probability of rejecting that claim. And importantly, P is not assumed, the prover is not assumed to satisfy any resource bound. So it is not even required to be computable. All we asked for the prover was that it was a function that given the input word and all the information that's a transcript of all the information that's passed between the verifier and prover so far in the interaction will then give the next bit of information to the verifier. So it just needed to be a function that would do that, that would interact with the verifier V, as we called it. So P can be arbitrarily powerful, but as I already said at the start, a remarkable thing is that if we're going to show that if you have a language that's an interactive proof, so if a language has an interactive proof, you give it a verifier, and the verifier has to work for some prover, which could be arbitrarily powerful. But it turns out there always exists an optimum prover, and that optimum prover, an optimum prover that satisfies completeness, and this prover is PSPACE computable. So even though we don't make the assumption that the prover is computable, there always exists one that is computable, and moreover, it lies in the complexity class PSPACE. And this surprising, I think, when you first see it, this surprising result is actually a byproduct of the proof, the main proof I want to do now before we have our first break, and that's the proof that IP is a subset of PSPACE. Okay. Has anyone seen this proof before, that IP is a subset of PSPACE? No. So it's just going to be an outline of the proof, but it's going to have the main idea, and that's the important thing. So it's hard to find a detailed version in the. I mean, I guess the original paper would have it. So we suppose we've got a language that belongs to IP, and we want to show it belongs to PSPACE. So we've got a language that belongs to IP. In particular, we have a verifier for it, and that's a polynomial time a probabilistic polynomial time algorithm, the verifier. And what we want to define is a deterministic polynomial space decision procedure for L. So let me go to the picture here, and I'll explain it first in the picture, and then we'll go back to the words. So what we want to do is construct we want to construct a polynomial space decision procedure to say when a word W belongs to the language L. And we've got this probabilistic polynomial time verifier, which by exercises in the probability exercise class, on the probabilistic algorithms exercise class, the probabilistic polynomial time verifier might as well be run in not just expected polynomial time, but can be in a long worst case polynomial time. So there's a polynomial that bounds every branch. So what we do is we want to decide an input word W. And what we're going to do is basically simulate every possible interaction that the interactive proof can make on an input word W. We know what the verifier does. So the verifier takes in W and is a polynomial time probabilistic algorithm. So with some probability, it'll produce one result or another result, or there might be many possible different results the verifier will produce, all of which are inputs to the prover. Well, we don't have a prover at the moment, but all of which are inputs to whatever algorithm we're going to have interacting with the verifier. So we have a probability distribution over messages the verifier can come up with. Okay, and those messages will be passed to the prover. And the messages the verifier can come up with, they're always in our alphabet. I mean, to begin with, part of the definition of the interactive proof is we have some polynomial that bounds the message length. Okay, both for prover and verifier. So we've got a probability distribution over all words of size of length, that polynomial of the input word length. So this is just the round one of the verifier. But after round one of the verifier, the verifier will interact with the prover, and we don't have a prover in mind. So what we're going to do is we're going to consider every possible thing a prover can do. So these branches represent every possible thing. So prover is a function that will, given the input so far, will produce a message U for the verifier, again of the same length, polynomially bounded in the input word W. And these red, so here we're building a tree, and these red lines here represent every message that any prover or false or fake prover might pass to the verifier. And then again, when the prover passes such messages, we go, so here we're not running any algorithm here, we're simply considering a tree that branches with every possible message prover might produce. Then we go to the verifier step. We again run the verifier's algorithm on on the given output from the prover in the first round here. And again, we get a probability distribution over messages that the verifier might pass to a prover, or maybe sometimes the verifier will accept, or sometimes it will reject. Or if it doesn't, it will have a message and it will give it to the prover, and the prover will, and then again, we don't have a prover, but we consider every possible message the prover might pass to a verifier and carry on. So I haven't finished the tree, but here we would carry on with more V steps. Let's just stick a V in there. So we repeat this until every branch is complete, so to speak. So this is an absolutely huge tree. At every step, we're branching with 2 to the power of polynomial in the size of W different branches, potentially. And at the V steps, there's a probability distribution over them. At the P steps, there's no probability distribution. It's just different messages a potential prover might provide. So there's no way we can fit this tree into polynomial space. But what we can do in polynomial space is we can go down any branch of the tree, because the length of the tree, the length of the branch is polynomially bounded. That was one of the requirements of the verifier, that of the polynomial proof, that the number of rounds is polynomially bounded in the input side. The length of so the length is polynomially bounded, and at each stage we have just a bit of data of size P of W. So we've got the product of 2 polynomials here for the size of all the data needed we need to store on a branch. So we can record, we can go down a branch and we can record all the information we get on the branch. And then once we get to the end, we can backtrack and go down the next, see where we've got the next choice point and go down the next branch, because we've recorded the information we've got for this branch, and we can see what the next one is, and so on. And also, as we go down the branch, so here we're simulating the verifier. That's what we're doing. That's really what gives us the branches. The verifier is going to make probabilistic choices. And as we simulate the verifier, we keep a track of the probabilistic choices and see what probability weight they get. So if it tosses a coin, each of those, and also again by the exercise classes, without loss of generality, we can consider a verifier that only tosses fair coins. That simplifies things a bit. So at each time it makes a step, we record that the probability of the current branch reduces by 1/2. And so we always keep track of the probability of going down the current branch. And what we want to do is we want to compute the maximum probability that a prover can have of nudging the verifier, encouraging the verifier towards accepting as much as possible. Okay, so what's the best option the prover can take at each step so that the verifier will accept with the highest probability? Well, we can compute that from the leaves upwards by, we're working out probabilities as we go along. And what we want to do at each V step is take a weighted average over the probabilities of the values we get from below. But over the P steps, what we want to do is we want to push verifier in the most likely direction to succeed. So at the P steps, we choose the branch that's going to have the highest value below. So we think of this tree as computing a value. Every V step, every V node is a weighted average, and every P node is a maximum. And that can be computed from the bottom up. But moreover, that value can be computed by traversing the tree one branch at a time, by recording the current information for the node for each node as we're at the node, and then as we get more probabilistic steps, we add to the probability here, and here at the P node we have the current maximum for the branches we've considered so far, but if we get a higher branch, we'll sort of update our maximum. So this idea of computing the value, maximizing over the V node, averaging over the V nodes, maximizing over the P nodes, we can compute that in polynomial space. And when we compute that in polynomial space, well, the value we get at the end is the value that is the probability of acceptance that the verifier will have if it runs against a prover that encourages it as much, the verifier as much as possible to accept. And actually that value, when we've computed it, there are only two possibilities for it. It can, if we started off with a word in the language, then that value is guaranteed to be greater than equal to 2/3, because for the actual prover that is there for the language to be in P space, the probability is greater than equal to 2/3. So for the prover that maximizes this value, it's certain to be greater than equal to 2/3. And if the word's not in the language, well then whatever possible prover we had, the probability was guaranteed to always of acceptance was always the probability of acceptance was always guaranteed to be oh sorry, we're only interested in the word in the language here. No, we're not. So, no, sorry, what I was saying before was right. So if we have a word that's not in the language, then whatever the prover does, the verifier can only accept with probability at most 1/3. It rejects with probability at least 2/3. So the value will always be less than equal to 1/3. So there's quite a dichotomy here. We'll either get a value greater than equal to 2/3 or less than equal to 1/3. In the one case we accept, in the second case we reject. And from this search of this tree, we also see how we can in polynomial space provide our optimum prover, because we're computing these we're computing these optimum values here, and at the same time we'll just always for the prover record the branch that gave the maximum value, and that is then a polynomial space algorithm for the prover, for the optimum prover. Okay, so we're done, and with that proof, so we have shown that IP is a subset of P space. And now I want to go after the break to the main theorem, which is that, which is that IP equals P space, but the main result we're going to show is that the truth of quantified Boolean formulas is an IP problem, has an interactive proof. Okay, I'm going to pause the recording now. Because of time reasons, I want to finish the lecture early, so I'm going to just have a break until 1/4 now and start again at 1/4. Let me pause the recording. Are there any questions? Right, so the main theorem then today is that true quantified Boolean formula, well, actually the main theorem is really the corollary here, that IP equals P space, but we've shown that PSPACE, we've shown that IP is a subset of PSPACE already, so we need to show that PSPACE is a subset of IP. For this inclusion, we observe that if you have any language L prime that's polynomially reducible to a language L that has an interactive proof, then, so if a language L has an interactive proof, then any language that's polynomially reducible to it also has an interactive proof. So I've not put the argument for this, but it is almost immediate. So your interactive proof is basically the same. It is your interactive proof for L is also an interactive proof for L prime. You just need to, all you need to do is translate the inputs. There's almost nothing to show, but you can think about that in your own time offline. But basically, it's almost trivial. So if you have a language in IP, any language that's polynomial time reducible to it, it also belongs to IP. So that means if we have a PSPACE hard language in IP, then every polynomial space language is also in IP. As we saw at the start, Tqbf is PSPACE hard, so it's enough to show that Tqbf has an belongs to IP. In other words, that the truth of quantified Boolean formulas has an interactive proof. So that's what we want to do. We want to provide an interactive proof for the language, well, for the problem, show that a quantified Boolean formula is true. Now I'm going to follow the approach that all expositions of this I have seen follow, which really makes a lot of sense because it's a very complicated proof, this. And in order to understand what's going on, it's actually much easier to understand a simpler case that has most of the difficulties, but not all the difficulties in. And then after that, sort of do the extra work that's needed to understand how to go from the simpler case to the truth of quantified Boolean formulas. So actually, we're going to begin by showing an easier problem has an interactive proof. And that interactive proof is this. I suppose I should use the proper notation. It's the problem sharp 3 sat sub D. So a bit of notation. So sharp sat means counting the number of satisfying assignments to a Boolean formula. We're going to look at this in January in more detail. Already one of the student presentations talked about sharp sat, the one on the permanent, a little bit. So sharp 3 sat would be counting the number of satisfying assignments to a 3 CNF formula. Sub D means turning that, so counting, you need to come up with a number as a result. Sub D means turning that into a decision problem. So to turn it into a decision problem, we give a target number K, and we ask, so counting the number of satisfying assignments to a 3 conjunctive normal, a 3 CNF formula decision problem, we give as input the 3 CNF formula phi and a target number K, and the language that belongs to the language if K is the binary representation of the number of satisfying assignments of the formula phi. Okay, and this, the size of K here is, well, O of the size, big O of the size of phi, or even pretty smaller than the size of phi, because if phi's got n variables, then it has at most 2 to the n satisfying assignments. So one needs fewer bits to represent the number of satisfying assignments than one needs to represent the whole formula. And what we're going to show is that this problem of counting the number of satisfying assignments of a 3-sat formula has an interactive proof. That might not seem very related to Tqbf, but here's a special case of Tqbf. So unsatisfiability is a special case of Tqbf where you're considering just universally quantified, a quantified Boolean formula that's universally quantified. So a propositional formula phi is unsatisfiable if and only if the universally quantified version of the negation of that formula is true. Okay, so that's how to turn that to Tqbf. And then, well, you can see how to get that in terms of actually. So what I've just said isn't quite what you need. So if you can count the number of satisfying assignments, well, you'll see that you can tell if a formula is unsatisfiable or not. Okay, sorry, I was just a bit confused. I don't know why I was introducing true quantified Boolean formula there. If you can count the number of satisfying assignments, you can tell if a formula is unsatisfiable, and that's an exercise. Okay, so the warm-up theorem is to show this problem of counting the number of satisfying assignments of a 3 conjunctive normal form, that has an interactive proof. So this is the warm-up for the main theorem, but the proof of this is going to take 5 pages. So it's quite complicated. But let's work with a simple example. But I'm not going to push the example all the way through. It's just to motivate things. We're not going to get to the end with this example. So we want to count the number of satisfying assignments of a 3CNF formula. So a 3CNF formula, every clause has 3 literal, at most 3 literals. So like this one, we've got 2 clauses, each has 2 literals. And the first thing we observe is that Boolean formulas, propositional formulas, can be represented as polynomials. So for a formula phi with n propositional variables, we can represent it as a polynomial over the integers, f of phi with n variables. So this is the polynomial for this formula. So essentially what we're using is that multiplication on 0, 1, on the value 0, 1, is the same thing as conjunction of truth values. And 1 minus a value 0, 1 is the same as propositional negation. And conjunction and negation are enough to get all the propositional connectives. In particular, or is defined by the De Morgan rules that A or B is not the negation of not A and not B. So here we've got a disjunction. So that's the same as the negation of the conjunction of the negations. And because negation is 1 minus, and the conjunction is multiplication, the negation of the conjunction of the negations is 1 minus the product of 1 minus the values. And this is 1 minus 1 minus, so it just becomes x2 because this was negated. So you can see this represents this clause. Here we've got an and, so that's a product, and this represents this clause. Okay. So if phi has m clauses, we're going to use n for the number of variables and m for the number of clauses. If phi has m clauses, well then this polynomial in general, f of phi, that's formed in this way, is going to be each clause has, I'm going to look at the degree of the polynomial, so how many variables appear multiplied together in each monomial in the polynomial. So because you've got most 3 things here, the degree of each clause is at most 3. You've got m clauses, so the degree of the whole polynomial is at most 3 times m. And what we've got with this polynomial, the general property is, so we've translated a formula phi into a polynomial f of phi, such that if we plug in values 0 and 1, for the truth value, 0 is false and 1 is true. If we plug in values 0 and 1, if we evaluate the polynomial, it's the same thing as evaluating the propositional formula. That's how this thing works. So then the number of satisfying assignments is simply a sum over all Boolean values for the n different variables. So 2 values for the first variable, 2 values for the second variable, and so on up to the 2 values for the nth variable of this formula. Because this sums over all 2 to the power n possible assignments to the values. And this formula will be 1 when it's a satisfying assignment and 0 otherwise. So we're exactly summing together all the ones that correspond to satisfying assignments. Okay, so I mean, a first basic question would be, well, why don't we just compute this sum? But the reasons should be hopefully fairly obvious, which is we've got we're summing over n different truth values. So if we do this as a nested for loop, then we're summing over 2 to the n different things. So we can't do that efficiently. So in fact, there's no obvious efficient way to calculate this value. And as we'll see in January, there's a complexity class about how hard it is to calculate this value. So it's called sharp P, which is quite a hard complexity class. But in any case, what we can see straight away is that this is, if P is not equal to NP, we certainly can't P time compute this, because we could decide satisfiability if we could P time compute this, because the formula would be satisfiable if and only if this value is not 0. Okay, so it may not seem that we've done very much. We've reduced a propositional formula to a polynomial that computes the same value over the values 0 and 1. But what this does get us is, it turns out that computing the value of a polynomial is a problem we can give an interactive proof for. So although the problem is not obvious how to compute this efficiently, it turns out we can give an interactive proof where the prover is going to convince us that a value, that this sum of over the Boolean instantiation, the 0, 1 instantiations of variables of a polynomial, that this sum has a particular value. So we want to now turn this into an interactive proof that the prover is going to convince us of this. So we're going to, so we'll see how that works in a moment. But I want to just make the step into this. So this is how we're going to do an interactive proof to show that a particular formula in conjunctive normal form, in 3 conjunctive normal form, and a particular number, target number k, belong to sharp 3 sat sub d. So in other words, that phi has exactly k satisfying assignments. So this is going to be an interactive prover between the prover and the verifier. Actually, the prover starts in this one. Of course, although I had in the definition of interactive proof, the verifier starts, it doesn't matter. The verifier can just send a dummy message and the prover can then go next. So the prover starts, and the prover starts with something the verifier could also do for themselves, which is, but it's sort of nicer to give this to the prover because they've got more, they can do it more easily. They've got more computational power. So the prover sends V a prime P that's bigger than 2 to the n, and we don't want it to be too big. In the textbook, it's between 2 to the n and 2 to the 2n, which means it could, if wanted, be efficiently found rapidly. But since the prover actually has unlimited power, I'm going to put it in the interval from 2 to the n to 2 to the n plus 1, because there's a nice, side remark. There's a nice result in number theory called Bertrand's postulate that says for any number greater than 3, there's always a prime strictly between n and 2 times n. So that's saying there is always a prime, some prime in this interval that the verifier can find. Okay, so the verifier can find a prime, doesn't matter how they find it, but they're going to give it to the, sorry, not the verifier, the prover that has unlimited power can find this prime, doesn't matter how they find it, they're going to send it to the verifier. Now, the verifier doesn't want to be, we don't want things to fall down because this is not a prime number. So the verifier first checks that P is prime, which it can do in polynomial time. Can do it exactly in polynomial time because we had a student presentation about the AKS polynomial time decision procedure for primes. And the verifier is going to reject if P is not a prime. So yeah, the prover needs to send a prime. And why do we need this prime at all? We need to distinguish here between the capital P and the little p that's the prime, but why do we need this prime at all? Well, what we're going to do, we're going to reduce the problem to talking about polynomials, and the verifier is going to ask P to convince it now. So the way the interaction is going to work is the verifier is going to continuously, repeatedly ask the prover to convince them that a certain polynomial has a certain value. And that turns out to be the problem that we can get into a nice interactive proof working for. And so we first turn the counting the number of satisfying assignment problems into that using what we had on the previous page, which is the verifier is going to then say to the prover, hey prover, please convince me that the sum over these n Boolean variables of this polynomial f phi that I've constructed from the formula phi is the input number k. But for this algorithm to work, everything needs to be done modulo some prime number p, because we're going to compute all polynomials for things to stay efficient and for us to be able to particularly understand the rejection possibilities. We're going to work in a finite field, a Galois field, the field of numbers between 0 and p minus 1, the multiplicative field of numbers between 0. Well, it's not multiplicative, it's a field, so it's additive and multiplicative. But anyway, the field of numbers modulo integers modulo p, which I'm just going to write fp for somewhere. Maybe I've got that notation somewhere. Anyway, so the verifier says, hey prover, convince me that this sum over values of this polynomial is the claimed number k. And because p is greater than 2 to the n, and there are at most 2 to the power of n satisfying assignments, because there are only 2 to the n many assignments to n different Boolean variables. This number, I mean, k needs to be between 0 and 2 to the n to start with, otherwise if it's a non-starter, you can just rule it out. So we can assume that k is less than or equal to 2 to the n. Because p is greater than that, this modulo p actually does nothing for so this value is guaranteed to be less than or equal to 2 to the k, so it's guaranteed to be less than p. So checking this equality modulo p is the same thing as checking it in the integers. Okay, for the moment. We're going to then go to other polynomials where it might not be the same. But for this one, that's all we need to do to check it modulo p. Okay, so checking equality modulo p is the same as checking equality in the numbers. And we also note that this polynomial f of phi, so it's quite a complicated polynomial. It's got lots of, so its degree is at most 3 times m. but it's a product of m things, each of the form 1 minus something. And if we actually tried to multiply this out and get the coefficients, then we get into an exponential blow up. So we don't want to multiply it out and get the coefficients, but nonetheless, for any given tuple of values, we can compute it efficiently just by going through each operation and computing every operation modulo p. So the verifier can compute the value of this polynomial efficiently, and the degree is bounded by 3m, which I'm going to call d. So we've always got the degree d less than or equal to 3 of m, and the v can evaluate the polynomial in. Okay, so those are important properties. And now I want to go through the main bit of the protocol, which is how the prover can convince the verifier that the sum over Boolean values of a polynomial that v can compute the values of equals some given constant modulo p. That's the main bit of the protocol. So now we're going to abstract away from the particular polynomial we've got, because this needs to work now for any polynomial, and it's going to be a recursive procedure, a recursive interaction that works for any polynomial, and the polynomial is going to change as we do, which is why so now suppose we have some polynomial in n variables, and this is a polynomial over the field of numbers strictly less than, so of numbers modulo p. So which I'm writing fp for, z over p or gfp, or different notations for this. So suppose this polynomial has degree d, and this degree is never going to change throughout the interaction. That's an important point. It's going to be important that we keep the degree. I mean, it can go, yeah, it might change a little bit, but it's never going to go above d. And the polynomial, the important property is we may not have it given out, expanded out as its coefficients, but v can evaluate the polynomial in polynomial time for any tuple of values. So what we want to show is how the prover can convince the verifier that the sum over Boolean values of the polynomial g is some constant c. So this isn't necessarily the input constant now k, it's just some constant c modulo p. So how do we do this? Well, what p does is p is going to say, I'm going to tell you, verifier, what this polynomial is. So this is the polynomial summing, let's expand it a bit. So we're trying to compute the sum over all n Boolean values of g of b1 up to bn. But what p says is, I'm going to tell you what the polynomial is for if we just consider the first of those variables, if we leave that as a variable and we just sum over the remaining n-1 values. So this is some polynomial. It's a univariate polynomial. It's only got the variable y in it. And p is going to send the coefficients for this, this polynomial h of y. Now, h of y is a degree at most d polynomial because g was a degree at most d polynomial, and we're summing instantiations of degree at most d polynomials. So it can have various powers of y in it, but the largest power of y it can have is at most d. Actually, you can get a sharper bound than that, but this is fine for us. And p sends to v, so there's no way v can verify this. V can't compute this sum. There's no way v can check that. I mean, check properly by algebra that what p sends is indeed a polynomial here. But p is going to send v just the coefficients for this polynomial. So it's a univariate polynomial. So it's going to be like some constant plus some coefficient of y plus some coefficient of y squared plus all the way up to some coefficient of y to the d. Okay, so p sends that many coefficients. So this again is a polynomial that V can efficiently evaluate this H. And what V does is V checks whether this is a plausible polynomial for this. And for it to be plausible, I mean, P is claiming that the sum over all n values of all the g's is C. So for it to be plausible, if we compute h of 0 plus h of 1, then h of 0, that's adding the value with b1 equals 0, and h of 1, that's adding the value with b1 equals 1 here. So h of 0 plus h of 1, if h of y satisfies this, h of 0 plus h of 1 is this sum, which should be C. So P is claiming that it's C, so we check that it is. So we check that h of 0 plus h of 1 is C, and if it's not, then P's been lying to us, and in that case we reject. So if this value is true, then we're plausibly P is telling us the truth. But what we want to do, we want to all the time, it's an interactive proof, we want to make sure that the prover is not tricking us. So we need to be as confident as we can be that P is telling us, the prover is telling us the truth. So what we're going to do is we're now going to randomly evaluate the polynomial H at some random value and ask the prover to then we want to use the fact that two polynomials are equal, this left-hand side and this right-hand side. If they're equal and they're of degree D, then if they're equal on D distinct values, then they're equal everywhere. So this fact, this is the Schwarz-Zipfel lemma. This was also referred to in one of the student presentations, the one on checking polynomial identities, which is kind of more or less what we're doing here. So if we're in the position that this might plausibly be the case, because we've calculated that h0 plus h1 equals C. So then we want to check it more by choosing a random value, and we want to check that this equality also holds for some random value R. And if it does, then with high probability, because the degree is low compared with the size of the prime number, which is large, so with high probability, this equality holds of polynomials. So we randomly choose an R, and if in the case n is 1, we simply check that h of R is g of R and reject and reject if it's not. So that's an easy case. But the interesting case is when the number of variables is greater than 1. So then what we want to do, so if the prover was telling us the truth, then when we instantiate this random value, then the sum of the n-1 remaining variables to g with the random value plugged in should be the same as h of R. Okay, so we want to know that that equality is true. If that equality is true, then we're happy. But how do we check that this equality is true? Well, this again is something we can't check efficiently for ourselves, because we would have to sum over the 2 to the power of now n-1 different instantiations of the Boolean values here. So the point is we're going to recursively ask the prover, this is a problem of the same kind that we had before. Sorry, I should put in modulo p here. This is a problem of the same kind we had before. The sum over some Boolean values of a polynomial is some constant modulo p. So we simply recursively appeal to the verifier, sorry, not to the verifier, to the prover to convince us that this equality is true. And this is just a recursive thing, so we ask the recursively appeal to the prover. So the prover again sends us coefficients for now the univariate polynomial we get from putting y in for b2, And again, we check that that has the right value on 0. If we add the 0 in one case, we get the value h of r. And otherwise, we choose another random value now for B2, and we keep on going. Okay? So that's the procedure. It's a bit involved, but there you go. It's interactive, and the number of times one goes back and one repeats this interaction between P and V that I've said here is, so each time we're removing one of these sums, and we get a new question of the form showing that a sum over the remaining Boolean variables equals some constant modulo P. Each time we remove one of those variables, and so after n times round, we finally finish. Okay, so hopefully it's clear that the interactive proof always accepts in the case that the polynomial equation does hold, that this sum of over the Boolean values indeed equals this constant C modulo P. And the reason that's the case is, well, the prover is supposed to be cooperating with us, so the prover always gives the right polynomial h of y, and then this check always holds because h is the right polynomial, and of course for a random value r, this equality will hold because again h is the right polynomial, and again because this equality holds, when we go recursively to the prover will give us the right coefficients for the polynomial we get by plugging a y in for B2, and so on and so forth. And the prover will never, the verifier will never reject. Okay, so in the case, so we have completeness. If the equality holds, then the prover rejects, actually with probability 1. So maybe I should say that. So accept with probability 1. So in the case that the equality doesn't hold, then when will V reject? We now want V to have a high probability of rejecting. So V will always reject if the prover fails to provides a polynomial h for which the sum of h of 0 and h of 1 is not equal to the claimed constant C. So if the prover does that, then V always rejects. What we want to find out is what the highest probability that the verifier can accept with, and we want that to be, we want to bound that by 1/3. We want the highest probability that V can accept in the case that the equality is not true to be 1/3, because V needs to reject with probability at least 2/3. So a cheating prover, in order to allow V to accept, needs to always choose the polynomial h so that it adds up to the respective constant. So then the only way that V, the verifier, can catch the prover out is by being lucky enough to find random values that distinguish between the two polynomials. But random values that distinguish, the verifier can't actually check. So the random value here is 8. One gets h of r, the random value r, and we're looking at h of r. The verifier can't actually check this equality, but if this equality fails, then we again go into the recursive procedure, and again we want the verifier, the prover is going to find a value h that adds up to the right constant, which is now here. And again, the verifier needs to get lucky enough with the random value that it distinguishes it, and eventually when it gets down to the base case, it'll finally catch the prover out. So for the verifier to catch the prover out, we need to, on each of the n rounds, the verifier needs to be lucky enough to find a random value r such that h of r is different from this sum. But it doesn't need to be that lucky, because as the polynomials differ, they can agree on at most d values. And so the verifier only needs to be lucky enough to find one of the p minus d values. There are p values in the field. The verifier needs to only find one of the p minus d values that will keep these two sides distinct. Okay, so the probability of doing that in one round is 1 minus d over p. And the probability of then of the verifier successfully catching the prover out on all n rounds is then 1 minus d over p to the power of n. And this is sufficiently large. It can be made greater than or equal to 2/3 because p is greater than 2 to the n and d is less than or equal to 3n. That's the number of clauses. And each clause contains only 3 variables, and you don't need to have any repeated clauses. So the number of clauses is big O of n cubed. And as large as, as long as one's working with sufficiently large formulas, then this number is now going to be small enough. I didn't do the analysis of why exactly when this formula is small enough and why, but it's rather intuitive, and I'm going to leave that for now. Okay, so that's soundness. And that then completes the proof that, what was it? Of the warm-up theorem, that the number of the problem of deciding the value of the number of satisfying assignments does have an interactive proof. Right, I'm going to pause the recording. I didn't, right. I didn't start the recording, or, oh no, I did. I was just recording silence for a while. Anyway, right, okay, sorry that my mic was off, but I'm now going to complete the lecture, and I'm not going to take the full time. I want to show that truth of quantified Boolean formulas has an interactive proof, building on the ideas we had about reducing this sort of thing. So like counting the number of satisfying assignments to a Boolean formula, we're going to do something similar. We're going to reduce to evaluating a polynomial, or checking that a polynomial that you can't evaluate efficiently, but nonetheless getting the prover to convince us that the value of the polynomial is a certain value. So we need an interactive proof to convince the verifier of the truth of formulas of this form. We've got a prefix of n quantifiers, and then we've got a Boolean formula, a propositional formula with n variables, or as I said at the start, without loss of generality, that propositional formula can be in 3 conjunctive normal form. So a formula with at most 3 literals in each clause, and let's again assume we've got m clauses. So the first idea is to, again, we're going to arithmetize this using a polynomial. And so basically satisfiability is like having an existential Boolean variables. And now we've got existential and universal Boolean variables. So the basic idea, the most natural thing is again, replace the existential variables by a sum and the universal variables now by a product. So instead of for all exists, for all x1, there exists x2, for all x3, there exists x4, some Boolean formula. We can use the same polynomial that represents the Boolean formula. Again, sum for the existential variables and product for the universal variables. And again, over the integers, it's going to be true that psi is true if and only if the value of this is not equal to 0. Okay, because 0 works like a false truth value, both with respect to sum and with respect to product. Okay, so that would be a nice idea. And if this worked, then it would be a lot simpler. Life would be much simpler than it actually is. And there are two reasons this doesn't work. But the textbook only mentions one of them. But the first one seems to me crucial, and other sources do mention it. So I don't know if just the textbook overlook it or gloss over it, or whether one can really ignore it for some reason that I haven't seen. But anyway, the first issue that the textbook doesn't mention is the result value. Because we've got a nesting of products here, so a product, whereas a sum is essentially doubling the value each time, we're summing over two values, a product is potentially squaring the value each time. So if we've got n squarings, well, okay, if we start with 1, we're okay, but once we've doubled it once with a sigma, and then we've got, suppose we've got n minus 1, or n, let's say n squarings following that, the result value is now bounded by 2 to the power of n rather than by 2 to the power of n. And this is a problem because our prime, we want to do everything modulo a prime that we can get that we know that the value modulo the prime is the same as the value modulo the integers. And if we, in order to get that for something 2 to the power of n, the prime would have to be too big for us to represent polynomially in the size of the input. So that's a real issue, and this is the one that the textbook doesn't mention. What the textbook does mention is this issue, which also occurs, which is the intermediate steps of the protocol involve multiplying polynomials, because we've now got these product formulas, and the degree of the polynomials then is also not polynomially bounded. So the degree can now double when you product two formulas of degree d. If you sum them together, you keep the same degree. If you product them, the degree doubles. And so if you do that n times, the degree can go up to 2 to the power of n. Okay, so we've got two issues here. So the first problem is quite easy to deal with. So the first problem, instead of summing, what we're going to do is replace the sum with an operator. So the sum is computing the number of assignments, but instead of that, we're going to replace it with an operation on polynomials that actually computes the disjunction. And then the product is going to be computing the conjunction, and the sum is going to be computing the disjunction. So I'm writing this down as a co-product, let's say, an upside down product. And so the co-product of two values at A1 and A2, sorry, A0 and A1, is simply the sum minus the product. And this, of course, if you plug in 0 and 1 values, this can always computes the disjunction. All right. So this V is disjunction here, not verifier. The second problem is more interesting. So we're going to the recursive protocol of the interactive proof is going to involve multiplying polynomials. So we don't want the degree to go. We want to be able to keep the degree, or give it a maximum bound, and throughout the process, it's never going to exceed that bound. And what we observe is some very simple observation, which is we're only interested in evaluating our polynomials with summing and producting, or actually now co-producting and producting our polynomials over the Boolean values 0 and 1. And on 0 and 1 values, if you have a variable, it doesn't matter what power the variable appears in, it always takes the same value. So the value of the variable xi is the same as the value of xi squared is the same as the value of xi cubed, and so on. So whenever you have a higher power of a variable, we can simply replace it with the variable itself. In other words, we can always make each polynomial multilinear. So each monomial contains only products of distinct variables, but each appearing with just one, with the power of 1. So that's what we're going to do. We're going to consider only multilinear polynomials. But the problem with that is that, well, I don't actually know to what extent this could be built. I mean, it seems plausible to me this could be built more deeply into the protocol than it is, but well, no, forgetting that, but what I want to say is what we're going to do is we're going to nest co-products and products of polynomials here, because we want to, instead of writing pi sigma, we're going to replace the sigma with the co-products. Each of these involves a multiplication. So we're potentially increasing the degree of the polynomials, and we're introducing when we do that higher powers of variables potentially. And the problem is then how to systematically eliminate those higher powers in a way that we can do that systematic elimination and build that into the protocol. So what we're going to do is we're going to introduce a new family of operators that L1 up to Ln, each of which linearizes the polynomial in Li will linearize the polynomial in variable xi. So we introduce, so for a polynomial f with n different variables, Li of f is this polynomial, which is by definition linear in xi, because we're taking the xi variable out and plugging in the values 1 and the values 0. So we consider xi times f with the xi variable instantiated to 1, and 1 minus xi times f with the xi variable instantiated to 0. And the point of this is, I mean, this polynomial is clearly linear in the variable xi. And if we evaluate it on xi equals 1, well, we get this, which is f of x1 up to xn, including xi. And if we evaluate it on xi equals 0, well, this drops out, of course, 1 minus 0. So we get this f with the 0 in here. So if we evaluate this polynomial Li of f on xi equals 1 or xi equals 0, we get the same value as the original polynomial f applied to xi equals 1 or xi equals 0. So we're linearizing the polynomial in xi in a way that we don't change the value of the polynomial on the two values of xi we're interested in, the Boolean values 0 and 1. So to compute then, for all exists psi, which is what we want to do. We want to compute the truth of that. Instead of our simple way of writing that as pi sigma f psi, and we want to prove that this is some value that's not equal to 0, and then it's a true formula. So instead of that, we use, so here we've got f of psi. I didn't put the variables in because I ran out of space. We take f of psi, we linearize it in all 4 variables, which then means at the end we get to, so I wanted to make the point, once the polynomial is multilinear, then its degree is at most the number of variables. So it's at most degree n. So at this point we get down to a polynomial of at most degree n. And then we do our co-product for the sigma. And now we get a new polynomial out of that can now need not be multilinear anymore. So we've now got 3 variables because x4's dropped out. So we now linearize on x3, x2, and x1. And now we can do our pi. And now we've got for all. And now we've got a polynomial in 2 variables. Again, it's not linear because we've producted 2 polynomials together, but now we linearize in 2 and linearize in 1. We do the co-product, we linearize in 1. So we reduce to a nested combination of operations applied, and we want to compute that this is equal to 1. Right, because we don't need to just say not equal to 0 anymore, because this will compute the psi formula exactly, the value of the psi formula exactly. The other thing I want to say is that it's obvious that the length of this prefix here of operations we're performing is O of n squared. Right, so we've got n is 4 here, so we've got 4 plus 3 plus 2 plus 1 plus, anyway, so this is length. And what we're going to do is we simply adapt the previous interaction between V and P to have O of n squared interactions, taking the operators from the outside and going in, 1 interaction for every operation. So before we were dropping the sigma prefixes off from the left-hand side 1 by 1. Now we're going to start with the pi x1. We're going to then do the L1, then the pi x2, then the L1, then the L2, pi x. So whereas before each round, each interaction, we needed to know how to deal with a sigma, we say to the prover, convince me that this sum equals a particular, that this chain of operations equals a particular value. Now we say that again, but we're going to do it by the prover will send back a polynomial representing in which we linearize, in which we put in the variable y for x1, the univariate polynomial. It's going to send back a polynomial, and we check that this has the relevant, that this polynomial needs to represent everything apart from the outermost operator. So we adapt the previous interaction between V and P to have O(n) squared interactions, 1 for each operator. Pi coproduct or L of I. And when P comes back with its polynomial, then V checks, depending on whether it's a pi, a coproduct, or an Li. It either checks, well, in the case that it needs to check that a pi thing equals a value, then you simply multiply the two. You've got your H polynomial, the prover sends back, you multiply H0 times H1 and check that that equals C. In the case of a coproduct, you form the coproduct operation, so H0 plus H1 minus H0 times H1. And in the case of the linearization operator, you check the you check the definition of the linearization operator. And that's basically it. Filling in the details would take a bit more time, but the book doesn't really go into much more detail than that. And in some way it goes into less because it didn't address this first issue about the value 2 to the 2 to the n, which meant introducing this coproduct operator, which I guess is a substantive issue because other sources do include this. But as I say, I don't know, maybe there's a way that it can be avoided. So that's basically as much of the proof as I felt I wanted to give you. So that's it, and I think I shall sign out from. I shall stop the recording, and then if there are any questions, we can do some